Hello, welcome to today's lesson. Today we are looking at Euclidean geometry. Let's look at the circle geometry. Before we look at the theorems that goes with the circle, let us look at, this is a circle, it has a center, and let's look at the lines on the circle. So this line from the center of the circle to the circumference of the circle is called a radius. Now, one radius but many radii. So before we even continue, we should understand that the radii of a circle are equal. So in other words, as long as we see this as a radius and this is a radius, then we know they are equal. Right, so the next line that I want us to talk about is a line that divides the circle into two unequal parts, and we call this line a chord. Right, so let's look at some more of these lines. This is the center. So the line that divides the circle into two equal parts and it passes through the center, it's called a diameter. It's a diameter. So it divides the circle into two equal parts. Right, and then we also have a line that touches the circle at one point. So this we call a tangent. Right, so now this space that is made by the radii is called an arc, and the space that is made by the chord is called a segment. Right, now a chord and an arc might have two different meanings, but they might mean the same thing. For example, if I put A here and B there, I'm looking at this as an arc. But if I can draw a line from A to B, I will refer to this line as arc AB. So that is why in most cases we will use arc and chord interchangeably. So in other words, but we know the arc is on the circumference, the chord is the line. So this line here is a chord. If maybe I put a P here and a Q there, we can talk about a chord PQ or an arc PQ. So that's other things that we need to understand. So we will be dealing with these lines. Some lines not really talking about, we don't really talk about them, like the one that goes through and passes through the circle, we call it a secant. So this it's called a secant. So it's a line that passes through the circle. So but we don't really talk about it in the theorems. So we will be going straight into the first theorem involved, the first circle theorem. Right, the line segment joining the center of a circle to the midpoint of a chord is perpendicular to the chord. Now we are going to look at these words and see the diagram that we are given. So they're saying a line segment. In other words, we have a line which is joining the center of a circle. So from these words, we can see that we have a circle with a center. So we are given a circle with a center. Right, so we have a circle with a center, and then we also have a chord. So we have a chord. We must have a chord, and then we must have a line from the center. The line is joining the center to the midpoint of the chord. So we need to check. Let's assume that this equals to this, so this is the midpoint. So a line segment joining the center to the midpoint of a chord. So we have this, right? So we have a line segment joining the center of a circle to the midpoint of a chord. So this is the situation that we have. So let's write the given information. Let's say we have the center as O, and then we have the chord as AB, and then let's just put a C here. Okay, we have two angles there. Let's just have 1 and 2. Right, so this is what we have. And now we must prove, we are required to prove, RTP stands for required to prove. We must prove that this line segment, in other words OC, we need to prove that OC, the line segment, is perpendicular to the chord. So in other words, we must prove that OC is perpendicular to AB. Right, so that is what we need to prove. So we need to prove that OC is perpendicular to AB. We are going to, the first thing that we'll start with is the construction. Now, in Euclidean geometry, when we talk about construction, we mean added lines that were not necessarily there that will help us to prove our theorem. So that is we call construction. We must use the pre-knowledge, what we have learned in the previous grades, to be able to prove our theorem in this case. So we are going to, the construction that we'll make here, we want to be making use of triangles. So for us to have triangles in this, we will join a line from O to A. Okay, let's write it down. We want to join O, A, and also OB. So let's do it that way. So either we make use of a dotted line, or we can even change and make it a color so that we know that this was not originally there. So we join OA and OB, so that now if you check, now we have two triangles. So now we are going to prove. So now we are going to look at congruency between the two triangles. So let's indicate in triangle OAC and triangle OBC. Right, we are looking at anything that is common in these two triangles. It can be angles, it can be sides, but the most obvious things are, if we look at side OAC is the same as side CB, so we must give a reason, but this one is given, is part of the given information. Remember, they told us that this is the midpoint and it's even indicated. And we also have OC for this triangle and OC for that one, so we can just say OC, it's common. There is a common OC. Right, and then we also know that the radii of a circle are equal. So OA is actually equals to OB. They are the radii, one radius but many radii. So the radii of a circle are equal. Now it means, therefore, that we can conclude that this triangle OAC is congruent. This is a symbol for congruency. Is congruent to triangle OBC. Now we have to give a reason. Now in this case, we looked at this side and that side, and then OC, a common side, OB and OA. So our reason for congruency here is side, side, side. So we looked at all the three sides. So for more information on conditions for congruency, please watch the video above that deals only with congruency. Now that we know that the two triangles are congruent, then we can say now that we can say C1, angle C1 equals to angle C2 from congruency. Angle C1 equals to angle C2. But then C1 plus C2 is 180 degrees because this is a straight line. This is a straight line. These are angles on a straight line. These are angles on a straight line. So now we can come up with this conclusion that C1 and C2 are equal, and when we add them we get 180. It means each one of them must take a 90 because they're equal. Therefore we can conclude by saying C1 is 90 degrees, also C2 is 90 degrees because they are equal, and when we add them we get 180. So if C1 equals to 90 and C2 equals to 90, so it means that OC is perpendicular to AB. Therefore OC is perpendicular to AB, and by so saying it means we have concluded our theorem. Remember, for us to say we have proved the theorem, the required to prove must be the same as the final statement. So it was required that OC is perpendicular. We were required to prove that OC is perpendicular to AB. So thank you very much. Please don't forget to support me by subscribing, sharing and liking. Thank you very much.